In this video, we're going to look at maximizing problems involving the volume of a box. So let's say we want to start with a square sheet of sheet metal, and we want to make the largest possible volume of a box out of this. And we're going to cut equal squares, equally sized squares out of the corners and fold up the box. Let's actually look at this problem statement. Maximizing the volume of a box. Find the volume of the largest box that can be made from a 16 by 16 piece of metal. This is to be done by cutting out equal size squares from each corner and folding up the sides. And so in the box that we're looking at here, we could say maybe count each of these corners as being a square of x by x. So let's say that this is x, and this is x, this is x, and this is x. So we're going to find the volume by cutting out a square that size and folding up the sides and making a box out of it. So the original piece of sheet metal is 16 by 16. And we're going to cut squares out of the corner. As I mentioned, we can call the dimensions of those squares x by x. And again, we want to maximize the volume. So let's actually write the equation for the volume. Again, remember, whenever you're working with these maximum minimum problems, you have to write the equation or somehow get to the equation of the function that you want to maximize or minimize. So again, let's call the volume of the box V of x. And again, when we think we're going to fold these up, think of what we're going to have. We're going to have, so like the height, when we fold it up of the edge, it's going to be like x will be the height. If you can imagine folding this box up, it'll be x tall. And then the width is going to be 16 minus x minus x. So that's going to be 16 minus 2x. And then also for the depth or length, whatever you call it, like say over here, it's going to be 16 minus x minus x, or same thing, 16 minus 2x, like that. So the volume will be in that form. And so now we multiply this out. We're going to, like, if we FOIL this and then multiply by x, when you do that, you can double check this. I ended up with 256x minus 64x squared. Plus 4x cubed. Like that. So that's going to be the volume of the box, depending upon how big our x is going to be. So now again, whenever we want to maximize something in calculus, we take the derivative and set it equal to 0. So let's take the derivative. And so over here, this is going to be 256 minus, what's that going to be, 128. And this is going to be 12x squared, like that. Now, as it turns out, it looks like we can't, we could probably factor something out of here. Let's see, a 2, looks like certainly a 2 will factor out. And actually, a 4 will factor out 1. So let's take a look at that. So we can factor out a 4. And that leaves us with 64. And when we factor out a 4 out of here, this gives us 32. Factor 4 out here, of course, that gives us 3x squared, like that. That'll make it a little bit easier. As I said before, we want to set this equal to 0. And now it doesn't look like this can be factored. And even if it does, we can just simply use the quadratic formula. Remember, of course, this could never be 0. 4 is 4 is not 0. So the only way to make this whole expression 0 is to set this equal to 0. And so therefore, if we just focus on that, let me write it down that way so you can see clearly what I'm doing. So I want to set this equal to 0 and use our quadratic formula, negative b. Remember, in this case, I kind of wrote back, this is going to be a, b, and c. Negative b plus or minus square root of b squared minus 4 times a times c divided by 2a. And by the way, if you didn't want to factor out the 4, you could have done the same thing with this equation. You could just use the quadratic formula here, just set this equal to 0. It would have worked out exactly the same way. Just our numbers are a little bit simpler since we were able to factor out a 4, but you could have done it right here. So let's see what we get here. So I got 32 plus or minus 16 over 6. So it's going to give us, if we add the numerator, that's going to be 48 divided by 6, which is 8. Or, let's see, if we subtract those, that'll be 16 divided by 6, which is 2.677. Now let's think of this for a minute. If x is 8 and you put that into our volume up here, notice right here we'll have 16 minus 2 times 8, which is 0. So that's going to give us 0 volume. So obviously that's not the right answer. In fact, that would probably be the answer if we wanted the minimum. And so this other one must be the maximum. So we'll get the maximum volume. We're going to check that in a second here. So the maximum value will occur when x is 2.67. So again, let's check that using the second derivative test to see if that is in fact the maximum. So remember, if we want to do the second derivative test, go back to this equation here and take the second derivative. This was the first one. So the derivative here is minus 128 and bring the 2 plus 24x like this. And then remember, when you do second derivative test, we substitute our critical point into the second derivative and see if we get a positive or a negative. And that gives us a negative 63.92. So that means, remember, since it's negative, since second derivative negative, that means x equal 2.67 produces a max. Because you remember the second derivative tells you how the slope of the curve is changing. So that means at the maximum point, it's changing from a positive slope to a negative slope. And that's what this is indicating right here, that we're changing from a positive slope to a negative, and that occurs at a maximum. Let's just check the minimum just to verify that x equal 8 was the minimum. So minimum volume occurs when x equal 8. Again, let's put x equal 8 into the second derivative. So that was this one right here. And that gives us 64. So remember, if you have a positive second derivative, since the second derivative is positive, then x equal 8 produces a min. I guess in other words, we're coming down like this. We're changing from a negative slope to a positive slope. That's what's indicated by the second derivative being positive. So that's going to give us a minimum. So in case the maximum volume occurs when x equal 2.67. So the question is, what is that maximum volume? So the max volume, now we have to put this number back in the original equation. Max volume is going to be, we could put it in either of these equations. It'll be a little bit easier to put in this one. So let me put into that one. So it'll be 2.67. 16 minus 2.67. 16 minus 2.67, like this. And we put that in our calculator. And when you put that in your calculator, you get a volume of 303.41 inches cubed. So the maximum volume occurs when x is 2.67, when that corner's a 2.67 square. And the maximum volume you get is 303.41. And the minimum occurs when x is 8. You'll actually get a volume of 0 in that case. Remember, we put that in. If you put 8 into here, this becomes 0. So this is typical of the kind of maximum or minimum type problems you'll have in Calc 1 using the first and second derivative test.